Hi there, and welcome to the screencast for Lab 2 of 193301. So today we're going to be looking at the chick weights data again that we looked at in the last lab, and we'll be looking at a few different plot types and sort of seeing how we can change things around a little bit. So first of all, I'm going to change the name up here to my name. So we'll put Solutions by Jonathan. Okay. And then we're just going to go through and sort of read through and then run the first few commands. I'm referencing the HTML file that has all the instructions in it that's on stream. Okay, so we're going to run this first code block first. Okay, and we see the sort of the top of the data frame here. Okay, and we have we can see it's got a weight, a time, a chick, and a diet variable. And this next code block is that we can run the summary. But first of all, let's just remember that we can run line by Control and Enter or Command Enter on a Mac. So if I run just the one line there, that data line, then that's creating that data set for us. But you'll notice that the output from the head command is gone. So when I run the head command next, I get the output, right? So you can run either line by line or by pressing the play button, we'll just run all the lines in the block. Okay, so this next line, let's run this. Then I get an error, right? And this is a very common error to get, which is why I've put it here. And it says error in summary chick weight. Object chick weight not found. And probably when you look at this, you're like, why not? Why can't it find chick weight? I've got chick weight, it's up here. And the reason it can't find it is because RStudio is case sensitive. So the uppercase and lowercase, the spelling matters, right? And here you can see I've used chick weight with a lowercase w. Okay, so just to be careful when you're typing things in, when you get this kind of object chick weight not found error, it's probably due to a typo. Not always, but most of the time it's due to a typo. Okay, so I could fix that by making that a capital W, and then the command will run and give us a summary. Notice that if I'm typing this in myself, so if I go summary and then put the bracket and start typing chick weight, then the actual spelling that I use doesn't matter for the case that I use, uppercase or lowercase, doesn't matter for the list that pops up. And so you can see here that chick weight is the one that I want. So I can then click on that and I get it right. Okay, so it's a kind of a handy thing to remember is to look for that pop-up as you're typing, because it can both speed you up because you only have to type the first 5 letters or whatever, and it can make sure that you can get the spelling right. So you can see here this is the summary. It's just the same as we did in lab 1. It's got the 5 number summary plus the mean for the weight and time because they're numeric variables. The diet and the chick are categorical variables, qualitative data, so it summarized those by producing a little table. Okay, so the diets are named 1, 2, 3, 4, which isn't particularly useful to us because we don't know what those diets mean. And then the numbers are the number of chicks or the number of measures in each diet, because of course we've measured each chick more than once. So chick 13 has been measured 12 times, chick 9 has been measured 12 times, and so on. Okay, so this is probably going to be sort of 9 or 10, 19 or 20 chickens. Okay. Right, so down here under the distribution of weights, we're going to start looking at how the chick weights are distributed. Okay, and so this is just looking at the single variable weight, and we're going to do a histogram. So you remember the recipe for a plot is we start with the ggplot, we tell it what data to give, then we tell what type of plot we want. So in this case, we want a histogram, and then you set up the mapping. So you set up the how you get from features in your plot to features in the data, or vice versa, right? So here we want the x-axis to be given by weight. So we want weight on the x-axis. The y-axis will be determined by the histogram itself, right? It's going to do the counting in each bin, and we get a plot that looks like that. So you can see that this data is clearly skewed to the right, right? Most of the values are bunched up on the left, and there's a long tail out to the right here. Okay. Right, so you'll notice that we've got this message here, okay, with the little I that tells you that it's information. Stat bin, using bins equals 30. pick a better value for the bin width. And so this is just telling you that it's sort of defaulted to 30 bins, right? And so we might want a different number of bins. So for example, we might want to use 15 bins. So notice as I added the bins thing here, I put it inside the histogram function, so inside the brackets for the histogram bit, because it applies to the histogram. I didn't put it inside the AES bit because it's not a mapping from our data to the plot, right? It's got nothing to do with our data. It's just a feature of it's just how the histogram is going to construct itself, right? So it's not, that 15 isn't taken from our data. It's just something that we've specified arbitrarily. And I've separated the two terms, the mapping term and the bins term, with a comma. Okay, so that's the sort of the usual construction. So the functions, like the histogram function, uses brackets to determine the parameters that you pass to it, and each of those parameters are separated by a comma. Okay, so we're changing to 15 bins, and so we get 15 bins, and the message has gone away as well, right? Because we've specified how many bins we want. Okay, and we could try other sizes, so let's try maybe 10. Okay, maybe 20. Right, so 20 is too many, I think, because we're getting sort of, a lot of noise here with that's probably not real, right? Because our counts are getting quite low down here. Maybe 15 is probably about right. 15, maybe a few less even. 12 maybe. Yeah, that gives us a feel. As I change it, my overall conclusion isn't changing, right? Most of the data is bunched to the left here, and we've got a few really heavy ones, right? So skew to the right data. So let's describe it. So the weights of chicks are skew to the right. Most chicks are bunched, have lower weights, less than 100, but a few are as heavy as 400 grams. So notice as I'm describing it, I'm saying what I think the statistical term is, skew to the right, but I'm also kind of describing it in just, regular speak language. I'm describing what I see, and that's just so that if I get the statistical language wrong, right, I'm still going to be able to get some marks for this question, right? Because I know what I'm wanting, I just got the term wrong. And, I don't really care too much as a marker if you get the right term. It doesn't really worry me. I'm more concerned with, do you understand generally what's going on, right? So, I mark for, do you understand what's going on? Not, did you get the language perfectly correct? Okay. So what else might we say? So we might say something about the range. It's from about 20 grams up to almost 400 grams. Okay. So most less than 200 grams. Okay, so I'm sort of commenting on where most of them are, so where the center is. So kind of in this block here, I'm commenting on the range, and I'm commenting on the shape. All right. Now let's try some other plot types, but before we do, we'll just check that the document compiles. So we're going to press the knit button here. And what that does is it sort of goes away, it clears everything out, so it sort of starts fresh, no data loaded or anything like that, no packages loaded, starting from a clean slate, and it runs through and runs all your R code line by line, from the start, from the top of the document to the end of the document, and it then integrates all your code, your output, and your writing into a single document. So let's press that and see what happens. So it brings up this window here, and I get my document. Okay, and I can sort of scroll through that and see, here's my graph, and here's the other graph that we're going to work on later on. Okay, now if you get an error when this happens, so say for example I hadn't corrected this, so say I made a typo here. All right, let's put that as the lowercase w, which is obviously wrong, it's not going to work, and then I knit it, then I'm going to get an error, right? So error in ggplot. Object chick weight not found, right? So it tells me where the error is. I can click on it and it will take it to me, line 41. So it's somewhere in here, okay? And so now I can sort of debug it, right? I can figure out what's going wrong. So for example, I could try running the line and I get the same error, okay? So that tells me that that, I've got a problem to fix, and I guess it's the same problem. So what I'm going to do is I'm just going to click on check weight, and I'm just going to fix up that problem so that it works, and then of course I'll be able to knit the document. Okay. When you knit the document, what it does is it also saves the markdown file for you. The HTML file that it produces then just goes next to it in the same folder. Okay, so you've got both. You've got the markdown file, and then you've got the output that it produces. Okay, so let's try some other types. What we're going to do is we're going to create a new code block, and we're just going to copy and paste the commands from it. So to create a new code block, you can go Insert R. Okay, and it creates these little sort of fences, if you like, with the backticks in order to describe where the code block starts and ends. And we're going to copy and paste that line and put it down here, and we're going to change the plot type. So instead of using a histogram, we are going to try a box plot. Okay, now we're not going to need the bins anymore because that applies to the histogram, right? Not the box plot. And there we go, there's a box plot for those data. Okay. So again, our conclusion from this is going to be about the same, right? So most of them are sort of between, are sort of in the box, really. So half of the observations are in the box, right? So you can see that it's going to be skewed to the right again. We've got the long tail out to the right. Most of the observations are in this range here. Sort of less than 200-ish is most of the observations. Some of them are almost 400, and some of them are as low as sort of about 20. Our conclusion is essentially the same for these data. Now, the advantage of a box plot is it's easy to compare groups, right? So we could actually add another variable in here for y as the diet, and that will then, instead of just having one box plot, it'll have 4, right? And so we get 4 side by side, and we can compare the diets. Okay, so maybe our conclusion here is diet 1 maybe has a little lower center, but there's lots of overlap between them, so hard to tell for sure. Diet 3 tends to have the larger, diet 3 and 4 tends to have the larger ones. And I guess all the diets are distributed skew to the right. Most values low weight, a few high weights. Okay. Another one we could try is a density. Right, so we're not going to have, so there's the density, and so that's similar conclusion to the box plot, right? There's the box plot, there's the density. So it's basically like a smooth form of the box plot, and the advantage here is that we can sort of do multiples. So you can do a couple. So there's a couple ways to do it. You could do you could change the color by diet. Right, and it'll produce 4 different lines, one for each diet. Because it's a distribution, really what you're looking at is the area underneath the curve, right? Because this is similar to it. You're using the height information here to compare, so that you might think that this is a sort of a line plot, right? But that's not really what it is at all. It's a density. So it's actually slightly better, I think, if we use fill instead of color. So if you use, so color does the edge, right? Color does the edge, which is the line. Fill will do underneath. So fill will change the color underneath. I think that's probably a better way of doing things, although in this case, of course, they're all on top of each other. So we can't see through, we can't really compare them very easily. And so what you could do is you could add some transparency with the alpha. So alpha is transparency, the level of opaqueness versus transparentness. It takes a number between 0 and 1. So 0 is fully transparent, and 1 is fully opaque. Okay, so 0.5 is half and half. And so that just allows you to look through, right? So we can see through to the ones underneath, and now we can compare them. And so it's sort of a little bit interesting now that we can see that, diet 4 sort of has this much broader peak here than the other diets. And you see it a little bit in diet 3 as well. Diet 1 is, that second bump there is very small compared to the rest. Okay, so diet 4 seems to have a bunch of chicks that are less than 100 and a bunch that are sort of high 100s to 200 grams. Okay, so there does seem to be a difference in shape here. That's something that it was hard to spot in this one. Okay, but we can spot it here. So you remember with the box plot, you're kind of assuming that there's only one hump. In this case, that one hump is very broad in the 4, or maybe it's even 2 humps. Okay. So the density plot. Okay. So the use of the density when made transparent and coloured. Right, so the key differences between these plots is that the box plot allows you to easily compare multiple groups because you can just sort of stack them up, right, and do as many groups as you like and compare across them. But you are making the assumption that there's really only one peak, one mode in each of the groups. So you're sort of assuming that there's not 2 bumps. The density allows you to do a similar thing. It doesn't work for as many groups, so this is probably about the limit for groups. If you have too many other groups, it just gets messy and you can't really see what's going on as well. But it does allow you to compare shape a lot better than the box plot does. And we'll see how to do other stuff later on as well. Okay, so under this next heading, we're now looking at the relationship between weight and age, right? So age of the chick is going to be given by the time variable, right? So if we have a look at the chick data, I just clicked on it in the environment there, you can see we've got the weight changing through time, right, as the chicks get older. Okay. Right, so this next plot will show us that, right? So there we go. There's how the chicks grow through time. And now we're going to copy that same thing and add diet. But before we do that, we'll just sort of make a note as to what we see here. As chicks age, they get heavier. Right, but also the spread of the weights get a lot wider, right? When they're first born, they're all very similar in weight, but by day 21, there's a large range. this makes sense as they're on different diets, and will also have different characteristics, right? So you might expect the ones that get big early on are going to sort of stay big. They'll be bigger chicks, so they'll be able to sort of muscle in the food a bit easier and all that sort of stuff, right? So now we're going to continue this, but we're going to colour it by diet. So you remember we've got the X and the Y's in the AES because they're mapping from our data to the X and Y parts of the plot, right? And so what we want to do is we want to colour the points by the diet, so we want to map the colour of the points to the diet variable, which we can do like that. Okay. So we can see a difference in weight by diet. The red group, diet 1, tends to stay at lower weights, while the blue group, diet 3, tends to be higher, as does diet 4, purple. Okay, so we can see something about the difference here, but perhaps a sort of an easier way to compare the difference is just to compare them at the endpoint, right? Because after the 21 days, the diets are likely to have made a difference. So if we just look at the 21-day-old chicks, we can, we take away the growth factor, the growing factor, and we just see the final weight factor. So what we're going to do is we're going to insert a new R block, and we're going to copy and paste the code from the HTML document. There it is there. Okay, and let's have a look and see what this does. Well, this seems to be taking the chick weight data, and we're subsetting it such that the time is equal to 21. Notice that I use 2 equals here. That means is equal to, so is time equal to 21? So it's a comparison, right? A single equals we've used before all the time, right? That's setting something equal to something, right? So setting the X variable of the plot equal to the time variable in the data, setting the data for the plot equal to the chick weight, right? So for setting, you use a single equals. For comparison, you use a double equals. Right, so this is going to create a new data frame called the old chicks, which just has the chicks at day 21. So we have only 45 observations of 4 variables. Okay, we can do a summary on that, and you'll see that the time variable is always 21, right? The minimum value is 21, the maximum value is 21, all of them are 21. You see that the chick, we only have 1 measure per chick, and these are, only a few chicks on each diet at this point, right? So 10 chicks in diet 2, 10 chicks in diet 3, 4 in diet 4, and 16 in diet 1. Okay, so looking at this might allow us to compare things. Right, so let's try doing a box plot. So let's just write what this is doing. So this is, so we have taken out only the chicks, only the day 21. Rows in the data. This will allow us to compare final weight between the diets. Right, so now what we're going to do is we're going to create a box plot of that. So let's grab our box plot code. It's going to be up here, isn't it? Let's grab that, and we're just going to run the same command, but instead of using chick weight, we're going to use our subset, so our old chicks. So there's our old chicks. And now, of course, we can quite easily see that actually there is quite a large difference here in the average weight of chickens in each diet. So that diet 3 produces the heaviest chicks. diet 2 and 4 are then similar, though has a larger range or spread, and diet 1 produces the lowest weight chicks. Okay, so this is sort of similar to the conclusion we got before, but is much easier to see. In this plot here, we could tell that most of the chicks were small here, but you can't tell whether that's just because we've measured them more at lower ages or something, right? Maybe we measured the diet 4 chicks at higher ages, and so that's why they're heavier, right? So here, because we've measured everything at the same age, we can more easily tell the difference between groups. Okay. Now you've got to be a little bit careful here, because remember, we don't have that much data. We've only got 16, 10, 10 and 9, right? So be a little bit cautious about over-interpreting the differences here, because there's only a handful of observations. It's only sort of 10 here, and 9 here. So if you just sort of added 1 or 2 extras, or took a couple out, you might get quite a different shape for the box plot. Okay, so you've got to be a bit cautious of making too bigger generalizations about your population, your differences in the diet based on a plot with just a small number of points in it. So look for the big things. All right, so here I've pointed out the difference in center. I've said that these two are about the same in terms of center, even though this one seems to be a little bit higher. But I have pointed out that this one has a much broader range, right? So this one includes chicks that are less than 100 grams, whereas this one, it seems as though there's probably only 1 or 2 chicks that were less than 200. Okay, so I've pointed out the big things, but haven't made a big song and dance about anything else. I haven't mentioned shape at all, right? Because with this few data points, they could all be actually nice and symmetric. We just really can't tell from a box plot with this small number of data points. Okay, so lastly, let's see if we can sort of make it a little bit prettier. So maybe we could color by diet. Okay, so coloring by diet will color the outside of the box plots. Alternatively, you can fill by diet. So that'll color the inside of the box plots. If you want to change the colors, then you remember we did that in the first lab. So what I could do is I could load up my first lab document, and I could go down and I could see that I used this command here for changing the colors. So I could copy that in there. Now, when I run that, it won't work. Right, it hasn't done anything. I don't have purple, blue, seashell 2 and orange. I've got the same colors I had before. And that's because I've changed the color scale here, but I'm not using color in my mapping. Right, I'm using fill. So if I change the fill to color, then I'll get the colors that I want. There they are. Seashell, of course, isn't a particularly good one in this case, but you can see I've changed them. So the scale color manual applies to the color variable, to the color aesthetic of the plot. If I'm instead using the fill aesthetic, then I'll want to use scale fill manual. Okay, there they are there. Okay, so that's how you change colors. I think I mentioned last time how you find all of them. You can just type in a new code block and just type in colors, and it'll spit them all out. So you can pick one there. There's goldenrod 2. What does that look like? Maybe we'll use that instead of seashell. Oh, well, it's too close to orange. What about this one here? There we go. Ugh, yuck. But you get the idea. All right, pick some nice ones instead. Okay, so, and to finish, we're just going to knit the document just to make sure everything works from start to finish, just to make sure everything's reproducible. Okay, so there's the first stuff we did. And down here's our box plots of the old chicks, and there's my beautiful coloured one, and there's all my colours spat out at the end there. Okay, I can always remove the code block there at the end if I don't want that in my final document, right? So just remove that code block there. Where is it there? Just delete that. And then it won't be in the final document. Here we go. Okay.